Guys, welcome. This is Unit 2. So, with Unit 2, we're going to be exploring our first time linear equations and absolute value equations. We're also going to be doing a little bit of statistics. And in this unit, I really stress that you have your own graphing calculator at home. It will come in handy as we move forward in this class. Uh, so just a little bit about what we're going to do going forward. So you're going to have to retain that information that you learned about with domain and range and all those graphical characteristics like minimum, maximum, where a function is increasing and decreasing, and also just the end behavior, what's happening at the end of these functions. Are they stopping? Are they bounded by limits? Things like that. Okay. So just an overview. There's 3 sections in this unit: linear functions, absolute values, which we're going to do today, finding solutions to absolute value equations, and then scatter plots. So that's where the statistics comes in when we're using information in a real world sense. Just an overview of the expectations for this unit. We're going to be moving pretty fast pace here. So far, you guys are doing really great. You've made me really, really proud. I hope you don't feel rushed, but part of building the skills necessary for college and transitioning to life after high school is being able to keep up with the pace and being able to complete the tasks that you need to complete. Okay? So thank you for trusting me, and thank you for doing what you need to do. So we're going to go ahead and get started. Okay? So the first part we're going to do is linear functions and absolute values. Okay? This part kind of warm you up to what you need to be able to do going forward. So the first word you're going to learn about is the vertex. The vertex of a geometric object. A vertex is created, first of all. You need like a peak or something like a valley. So objects that have peaks and valleys would be, for instance, the absolute value equation. This has a peak. This is the vertex. And this has a valley. I refer to it as a valley. And I use real world words in that sense so you can get an understanding. These are critical points when you're using real life data. Typically, these are critical points because when you think about rockets, for instance, you want to know how high can you go sometimes. You want to know where's the peak. Where is the peak? You want to know that. You want to know that information because you have factors like forces and things like that. And if you get to a certain point, and particularly in space, you want to protect the rocket and make sure it works and functions. So if you get to a particular point in space, you use math to figure out what forces are going to impact that rocket. And it's going to be at a vertex or a height or a specific height. Similarly, if you're moving down really, really fast, you want to know at what place can you smooth out that ride so you're able to come to a stop. It works across disciplines. It works across activities, sports, music, lots of different things, and of course, math. But the vertex of a geometric object is identified as a minimum or a maximum. So here on a curve, the vertex is referred to as a maximum. On that absolute value equation, it's referred to as a maximum as well. Over here on this curve, this vertex is referred to as a minimum. Okay? And sometimes the vertex is a point and it forms a peak. And I just shared that information with you. I explained it to you. And sometimes it's at the bottom or the top of the curve, and it's shaped like a peak or a valley. Very redundant, but you get the gist of it. Okay? So when you look at the object and it's on a graph, you have something called an axis of symmetry. And basically what the axis does, the axis of symmetry divides a shape in half. The coordinate of this axis, of the line actually, the line is the equation of the axis of symmetry. So sometimes if it's vertical, it's going to be x equals a number. And if it's horizontal, it's going to be y equals a number. Okay? So we're going to do this. Okay? Now, the next part, the types of functions we're going to explore here. Linear equations are always straight lines. Those domains are always negative infinity to positive infinity. The ranges are always negative infinity to positive infinity. And the equation in standard form has an x and a y variable. Typically, line functions come in the standard form y equals x. Or, sorry, I wrote that incorrectly. I apologize. So, ax plus by equals c. And this is where a, b, and c, they all belong to the real numbers. That means they're just numbers. It might also come in slope-intercept form, where we have y equals m times x plus b. And m belongs to all real numbers. The parent function of a linear equation is always y equals x. Okay? Now, absolute value functions, they're not straight lines. These are your v-shaped functions. And graphically are in the shape of v's. The equation form has an x and a y variable. And typically these functions are indicated by the parent by a absolute value, that symbol. The parent function is y equals the absolute value of x. So far so good, guys. So far so good. Now, for the equation, we're going to do a transformation. For the equation, parent function equation, it's going to be y equals x for linear equations. The parent function equation for absolute values is going to be y equals the absolute value of x. And we're always going to be exploring transformations. But first, we're just going to draw the basic parent equation. So here, y equals x always goes through 0, 0, and it always goes through the middle of your graph. All the points are in sync. What I mean by that, if you hit 1, you're going to hit on the x-axis, you're going to hit 1 on the y-axis. You hit 2, you get on the x-axis, you hit 2 on the y-axis. Absolute value is a little bit different. It's always going to be on one side of the graph. So here, for y equals absolute value of x, you still map out the top portion of y equals x, but you also map out the top portion of y equals negative x. And if I flip it over, I'm doing a little bit differently, okay? The negative x values. Now, first of all, we're going to do the graphical characteristics of these new lines. We're going to look at the transformations. And it looks like this line transformed up 1, because here is the y-intercept. So if I'm going to form this equation, it's relatively easy for straight lines. I know I have a +1 there. My slope, on the other hand, I don't know what it is, but I can go ahead and find it. And I'm going up 2, so +2 over 1, 2, 3. So 2 over 3 times x is my equation, +1. Okay. Now the parent equation here is y equals x. The domain and range, easy peasy. Negative infinity to positive infinity for a domain, negative infinity to positive infinity for the range. Now, you never have a maximum or a minimum. Okay, so none. Is it increasing or decreasing? Well, let's map on the line and put our arrows going from left to right. If you look, this straight line is increasing all the way from the left to the right. So we just repeat the domain here, negative infinity to positive infinity. There is no decreasing interval here. But for the x-intercept, I'm just going to circle it. It's right about here. And remember I said you estimate. So between 1 and 2, between negative 1 and negative 2, I have negative 1.5, comma 0. And that's about correct. 2 divided by 3. No, 3 divided by 2. That's what it is. Y-intercept right here at 0, comma 1. My zeros, always what x equals, negative 1.5. My asymptotes, there are none on straight lines. There is no limit. There's no bounding behavior here. Now, as I go to the right, as I go towards the right, this is going upwards in an upwards direction. So the end behavior is towards positive infinity off the map. As I go to the left, it's a downward behavior. So the end behavior is negative infinity going off to the left. Okay. Now let's look at this absolute value equation. And let's see if we can kind of figure out what happened here. Well, if you look at your original absolute value parent function, if you look at the apparent function, it appears that it has moved to the right one. So my new equation here is y equals the absolute value. It moves to the right, so I subtract 1 on the inside of the absolute value. And then it appears that it has moved down 1, 2, 3. And if I look 1, 2, 3, I started at the vertex, it did. So minus 3. So it moved right 1, down 3. So the parent equation of absolute values is y equals the absolute value of x. The domain is always negative infinity to positive infinity when it's in that form. Now the range, you have to be cautious. You have to be careful here. Look at your most bottom point. What is my most bottom point? Where does it bottom out? Right here. It starts here and it's filled in because it's that curve is or the peak, the valley is continuous, and it continues upward no matter what towards positive infinity. So my range is negative 3 all the way up to infinity, forever and ever. And yes, there is a minimum. There's a minimum. So we're gonna underline that. Minimum is positive 1, negative 3. Is it increasing or decreasing? Well, let's look and use our arrows. And if I go from left to right, it looks like it's decreasing. And then at the vertex, so this is at positive 1, from negative infinity to positive 1, we're decreasing. Now, arrows going up from positive 1 to infinity, we're increasing. So this is my intervals of increasing and decreasing. So I'm going to write it in interval notation. And I have 1, comma, infinity, hard bracket because it's filled in parentheses, always for infinities. And then on the other side, I have negative infinity to positive 1, hard bracket. Now, let's look at our let's look at these x-intercepts. So here I have 1 here and 1 here. This is x, this is negative 2, this is 4. So x-intercepts in the coordinate form, negative 2, 0, and 4, 0. Y-intercepts, I have 1 here at 0, 2. So at 0, 2, I have my y-intercept. Okay? And zeros, this is what x equals, and for your x-intercepts, x equals negative 2 and 4. Asymptotes, there are none on absolute value equations, usually. My end behavior, as I move over towards the left, I am increasing towards infinity. As I move over to the right, my y values are increasing. So far so good. Let's move to the next page, okay? Now, this part, we're going to be using the characteristics that are given. They're in written form. If you can transition from this, you can do pretty much anything. So we're going to draw a graph of an absolute value equation, given some conditions. So on the given coordinate axes, draw a graph that fits the following condition. This graph is the graph of an absolute value equation. So it looks like this, or it looks like this, depends. It has zeros at -3, x equals -3. So here it's going to pass through there, and it has a 0 at this point. The end behavior, as described, it can be described as it goes towards the right, it's pointing down. So it's going in this direction. As it goes towards the left, it's pointing down. Where am I getting that information from? Right here, it's going towards the right. Right here, it's going towards the left. So it says label the vertex of the graph you have drawn as an ordered pair. So I'm going to create my vertex right here. This is my vertex. It's 0, 3. It's pointing down, so I'm going to create my lines here and make it symmetrical. And there is the graph. I did everything I was supposed to do, and I'm going to label my zeros. This is an x-intercept. Here's the x-intercept. Here's the y-intercept. All right. So, transforming absolute value functions. The formula for absolute value functions, well, the equation really, is y equals this. That's the parent function. Now, the formula, what does it look like in formula form? You're going to have f of x, f of x equals a. It's going to be, if it's positive, it's going to be pointed up. If it's negative, it's going to be pointed down. If this number is bigger than 1, if a is bigger than 1, it's going to vertically stretch and get closer to the x-axis. If it's smaller than 1, it's going to vertically shrink and get closer to the, vertically stretch gets closer to the y-axis, vertically shrinks, it opens up a little bit and closer to the x-axis. Now, let's get down to business here. If it's negative, it flips over the x-axis. If it's negative inside, it flips over the y-axis. And then plus or minus a number, h, that number moves it left and right. And then here, the number outside, plus or minus, moves it up or down. Okay? So those are transformations. Flipping, shrinking, dilating, sliding left or right, and sliding up or down. Okay? Basic transformations. Now, the equation of this, we're going to go ahead and draw the parent function for each one. So parent function looks like that. Parent function looks like that. Parent function looks like that. None of these appear to have shrunk or stretched. So the equation here, it looks like for the first one, it just moved. The vertex just moved. Every point just moved over 4. So I'm going to subtract 4 in my formula. I have y equals the absolute value of x inside of the bars. The domain always negative infinity to positive infinity with parentheses. My range starts at 0, goes up to infinity. My new vertex here is 4, 0. The transformations moves right 4 units. The next one, it looks like it moves right 2, so we're going to subtract 2 inside. And so y equals. And then it looks like it moved up 2, so I add 2. Domain, always negative infinity to positive infinity here. This new function starts at 2, goes up to infinity. Make sure you use a heart bracket over here. My vertex, my new vertex is at 2, 2. Transformations, moves right 2, moves up 2. Okay? Last one. The last one, looks like it's moving right 1, moves right 1. So my equation is y equals the absolute value of x minus 1, and then it moves up 1, 2, 3, 4, 5. So plus 5. Domain, negative infinity to positive infinity. The range starts up here. Oh, guys, did you notice it's flipped over the x-axis? So if it's flipped over the x-axis, you can't forget. There's a negative in front. So my range here is going from 5 to so that's incorrect. And why is it incorrect? To say 5 to negative infinity. Smallest numbers first. So 5 goes over here. Negative infinity goes in front. Parentheses, hard bracket. My new vertex is 1, 5. Transformations. Flips over the x-axis. Moves right 1. Moves up 5. Okay? Now, next part, we're going to cover graphing transform functions. The great thing about knowing what the parent function looks like, it's not hard to transform it. If my parent function, I'm just going to draw it in red for each one for the absolute value. If it's right there, it becomes easy to do the things that I need to do, okay? So parent function's in red. I'm going to do the new function in blue. And then, so if I have the f of x equals the absolute value of x plus 2, I'm going to move left 2. So my new vertex is here. And this is my new graph. This is f of x plus 2. This is f of x. All right? Now, here's my parent function. It's in red. My new function moves to the right 1, so my new vertex is here. And I just draw my graph. It's very simple, guys. And this is f of x minus 1. Sorry. It moves down. You know what? I made a mistake. I hope you guys see that I made a mistake. I moved left and right. That number is not inside of the bars. So it's actually moving up. Moves up 1. Easy to correct. And this is why I encourage you to use pencils when you're doing this kind of work in math, because you make mistakes. But you can catch them if you continue forward and see clearly what you're doing wrong. Here, I'm moving down. I'm not moving to the right. I'm moving down 1. And I make my function. I make my function fairly easily. Once I know what the shape looks like, this becomes easy. Next one, f of x equals negative absolute value of x. So it's just going to flip over. It's just going to flip over. Okay? Now let's talk about what the vertex is. Well, the vertex, the new vertex, the vertex of the transform function we have at 0, 1. It's right here. The axis of symmetry goes right through that x value. So x equals 0. That's my axis of symmetry. Where it splits it in half. The vertex for my next one is 0, -1. Axis of symmetry goes right down the middle. It's x equals -1. No, x equals 0 still. X equals 0 still. Next one, axis of symmetry goes right down the middle, splits in half, x equals 0. Vertex is at 0, 0 still, okay? We didn't slide, we didn't move, we didn't dilate. Next page. Now, we're gonna look at linear inequalities. This is a review for you guys. It's awesome. So, a linear inequality is a linear equation with an inequality symbol. Examples, for example, less than, greater than, less than or equal to, and greater than or equal to. These are our linear symbols. These are our linear symbols, inequality symbols. Well, not linear, but they're inequality symbols. So when we're graphing lines for linear inequalities, when you have y is greater than or y is less than, we're going to use the dashed line. It's a dashed line. You use a solid line when it's equal to. Y greater than or y greater than or equal to means you are shading in an upwards direction, which is above the line. Y less than or equal to means you're shading in a downward direction, which is below the line. Now, when you're graphing linear inequalities, the first thing you always do is you always put the equations in slope-intercept form. You cannot, it's a struggle. You got to have some mad skills to not graph this equation, to graph this equation when it's in this form where the x and y values, x and y's, are on the same side, okay? So we're going to use the slope to rise and fall after we get that. So over here, we're going to say the slope equals the rise over the run. The y-intercept is just that number, okay? So first, we're going to solve for this y value, this y term. So we're going to rewrite the equation. These are our steps. Rewrite the equation, okay? So I did. That's step 1, rewrite. Step 2, move the x term. Step 3, we're going to divide by the coefficient in front of y. Okay, so let's get it. Let's do it. So I move my x term, negative 2x, because this is in standard form. 2x minus 2x goes away. Negative 3y comes down. Greater than comes down. 6 comes down. Minus 2x's comes down. Divide by negative 3 all the way across. 3's cancels. Y comes down. And remember, when you're dividing by a negative number, flip the symbol. Make a note of that. Dividing negative coefficients of y, flip the symbol. Okay, so y less than negative 2 plus 2 over 3 times x. My slope here is 2 over 3. My y-intercept is negative 2. So I'm going to go graph my y-intercept. It's negative 2. And I'm going to rise to, I'm going to go up to, right 3, and make a point. Up to, right 3, make a point. Up to, right 3, make a point. If I want to go backwards, I go down 2, left 3, make a point, and I create my line. Now, is it a solid line? Well, it says less than, so this is a dashed line. This is a dashed line, so that's why you use the pencil, please. Use the pencil. so you don't make mistakes like I did. I often make mistakes, probably on purpose. So this is a dashed line, so that means it looks like this. To recognize that none of these points actually fall in the solution of this equation. Now, all my y values are less than, so that means I'm going to be shading in a downwards direction. I will be shading in a downwards direction, and I'm going to shade this way. So I shade in a downwards direction below the line, and there's my solution. Okay, so I'm going to graph the next one. It's in slope-intercept form, so I'm going to make my my slope is -4. When you get a whole number, just divide by 1, so I can tell that I'm going down 4, right 1. Y-intercept is at 1, so I start at 1 on the y-axis, and I'm going down 4, right 1, down 4, down 4. Oh, that's messy. That's messy. Just go down 4 units and then right 1 unit. I'm going to go opposite, up 4, left 1. And is it dotted, dashed, or is it solid? It's dashed because of the less than. And I shade below the line because all my y values are less than the line. Okay. Next one, I don't like the way this is written, so I'm going to flip this over. I'm going to flip this over and put f of x is, mouth goes that way, -2x is greater than -2x minus 2. So here's my y-intercept. It's at -2. My slope is -2, and I put a divide by 1 when it's a whole number. So I go down 2, right 1, make a point, and I go up 2, left 1, make a point, up 2, left 1. You just go in the opposite direction when you're going backwards. And I did that wrong again, so you cannot, this is a greater than symbol, it's not equal to, so that means I have to get rid of that line and use the dashed line. Okay, it's greater than, all the y values are greater than, so I'm going to shade above the line. I'm going to shade this section here. Okay, now last one, y is greater than or equal to -3. My slope, when there's no number there, my slope is 0. That means I'm going to be going left to right. This is a horizontal line. My y-intercept is -3. I'm going to go find -3. Horizontal line going through where y equals -3. It's equal to, so I can make a solid line. All the y values are greater than this line. So I shade above the line. Okay? Next part, we're going to work on writing linear equation, writing the formula for linear equations using the slope and the y-intercept. So, in order to graph linear inequalities, you have to be able to identify the y-intercept, b, the slope, m, and the type of inequality or line type and the direction of shading. So we're going to go with the line type first. So the line type is a solid line. This is a solid line, so I know my inequality is going to be greater than or equal to or less than or equal to. The shade of direction is going to tell me whether it's greater than or less than. So it's shaded below the line. I can pick a y value, pick one below it, and it looks like those y values in that solution set are less than. So it's not this one. It's going to be y is less than or equal to. Okay? Now, let's go back to things we want to find out. The y-intercept, I'm going to do it in red. Y-intercept here. It's at -2 equals -2. I'm going to pick another good point on this line and figure out my slope, my rise. So I pick another good point. Looks like they already did one for me. My rise, starting at that point, I go down 2. So -2 over 1. This equals -2. So my equation, -2 over 1 equals -2 if I simplify it. My equation becomes y equals, my shade direction is less than or equal to, -2x minus 2. Okay? We're going to do that on the next part. My shading is the green part, the green section. And it looks like this is below. This is below. So the line type is equal to, is y is less than or equal to. My slope, I don't know yet. My y-intercept, I'm going to pick it out. And it looks like it's at 0, 1, or plus -1, -1. So -1 here. My slope, picking another good point, looks like I go up 1, 2, 3. So up 3, so plus 3 over 1 plus 1 equals 3. So I have y is less than or equal to 3x minus 1. Next one, my line goes from left to right, so it's y equals some number. What's my y-intercept? It's -2. Now, this is not an equal to line because it's dashed, and all the values are below, so it's less than. Y is less than -2. Okay? Watch that over again if you're confused. How you write these equations, you're going to need to be able to do that in the Algebra 2. The next part, the last part of this, is the special cases for domain and range. So these special cases talk about vertical and horizontal lines. So first of all, linear relations. So horizontal and vertical lines are special cases. They are not functions because, vertical lines aren't functions, but they're special cases. So we have to be careful and cautious. So first, vertical lines are not functions. Vertical lines are not functions. They have so many repeating x values. Like the vertical line itself tells you point in case that it's not a function. The y values, or the range, go from -infinity to +infinity. But the domain is always just one x value. Horizontal lines are linear functions. They are. The range is always a single y value. The domain goes from -infinity to +infinity. Okay? So looking at a horizontal line, I know that the parent equation is y equals some number. Okay? The domain is -infinity to +infinity. The range, however, is only at, looks like 1.5. Y here. We're going to use set notation for this. Get a little bit of practice. Y bar, y equals 1.5. That means my equation is y equals 1.5. Period. Domain for my vertical line is at the x value. It's a single value. It's x bar, x equals -3. Range is -infinity to +infinity in an interval notation. My equation is x equals -3. Now we're back to absolute value functions. The absolute value function always has a domain that goes from -infinity to +infinity on the right. So this domain all the way across, -infinity, +infinity, -infinity, +infinity, -infinity, +infinity. Okay? My range, on the other hand, starts at the lowest point. Starts here, goes up to positive infinity. So it starts at 1, put a hard bracket, goes up to positive infinity. Here starts at, looks like 1, 2, 3, 4, goes down to negative infinity. So 4 goes last, want the smaller part first, negative infinity up to 4, hard bracket. And here starts at 2, goes down to negative infinity, so negative infinity to 2, hard bracket. All right. Now, last but not least, graphing the inverses of absolute value functions. The inverse of a function can be graphed by identifying a couple of points. You then switch all of the x and y values. You last graph and connect the dots to these new ordered pairs. So first we're going to graph the absolute value parent function. Remember, it goes through right through the middle of your graph. Always touches 0, 0 for your parent function. I'm going to table a couple of these points. I'm going to put a couple of these points in a table. So for my x's and y's, on the left I have -3, 3, -2, 2, -1, 0, and then 0, 0, and then 1, 0, 2, and 2. Okay? Now my inverse, I could just switch the points, x's and y's, 3, -3. It's my inverse, my new points. So 3, down 3, 2, down 2, over 2, down 2, 1, down 1, 0, 0, and then 0, 1, 0, 1, and then 2, 2, 3, 3, and so forth and so on. This is my new equation. This is the inverse of the absolute value parent function. Okay? So, given the following absolute value function, graph its inverse, we're going to pick some points. Here's a point, 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 and here's a point. So I'm going to make a table of these points, and then I'm going to do my inverse table. And then I'm going to use that inverse table to create my new graph. So vertex is at 2, 2. Going to the right, I have, let's see, I have 3, 3, 4, 4. Now, going to the left, I have 1, 3, and then 0, 4. So I'm going to create my new table for my new graph, my inverse. So I have 2, 2, 3, 3, 4, 4, then 3, 1, 4, 0. So going this way, 3, 3 up 1, 4, 0, and I can keep going. Here's my new graph. All I did was switch the two sets of points. The sets of points here. Okay, so that's the end pretty much of this lesson. So I'm going to ask, let's look at these last two questions. Is the inverse of the absolute parent function also a function? No, no, never. Well, in this case, no. How do you know they're inverses? Switch the x and y values. You switch the x and y values. Okay? That is the end of this lesson. It was particularly long. You guys are great. I hope that if we did this before weekend, that you have a good weekend. Please do your homework. It's the best practice you will get.